Hello everyone, my name is Andy Knight. You can call me Pandy for short. I am the Automation Panda. I'm a software engineer and test who builds solutions to testing problems. You can follow me on Twitter at Automation Panda, and you can read my blog at automationpanda.com. This tutorial is entitled Hands-on Web App Test Automation. I'm super excited to give it here online as part of PyCon 2020. In this tutorial, you'll learn how to build a test automation solution from the ground up in Python. We'll use pytest as our core test framework, and we'll use Selenium WebDriver to automate browser interactions with a real live web browser. This tutorial is broken up into 9 sections. Each section will have a small lecture piece and then a hands-on coding exercise for you to do on your own. I strongly recommend pausing the video for each of those coding exercises for you to work through on your own. If you happen to get stuck with the coding exercises on the way, I've put all of the example code in a GitHub repository with different branches for each section of the tutorial. So you can always refer to the working example, so to speak. This tutorial is meant for anyone who wants to learn more about testing and automation in Python. You don't need any test experience as a prerequisite, but you will need intermediate level Python programming skills. So, if you're ready, let's learn. Here's the agenda for our tutorial. I'll start off by giving an introduction lecture about web UI testing. Then we'll have 9 sections in which I'll do a little bit of talking and then y'all will do a little bit of hands-on code. In total, this tutorial should take about 3 hours to complete. Before we start the lectures, let's set up our code. Go to this GitHub link and clone the repository. It has all of the example code, as well as all of the instructions for the tutorial in the README file. So, pause here, clone this repo, do all the setup steps, and then continue on for the lecture. Now that you have your project set up, let's talk about web UI testing. How would you define testing? It's a word that's thrown around a lot in software engineering. I would define testing as an activity that seeks to identify goodness as well as badness in software products and features for the sake of holding quality high. Testing can be done manually by somebody banging away at the keyboard, or it can be done using automated test scripts that will interact with either the code directly or with the product or feature in a live deployment or environment. However, something I've noticed is that there is a major misconception about different kinds of testing activities. When people talk about testing, sometimes they speak as if unit testing is the only kind of testing that there really is. And that's not necessarily true. There are many kinds of tests. Unit tests simply test code directly in small bits, but we can also test live service APIs, or web UIs, amongst other things. I've seen this misconception in a number of places. For example, it appeared in the Python Developer Survey of 2018. Now, I'm very, very thankful for JetBrains and for the Python Software Foundation for having this survey. When I took the survey in 2018, I was really excited because I saw a question about testing frameworks. I think the question was phrased something akin to, what testing frameworks do you use in Python? However, when the results came out and I read the report, I noticed that in the verbiage around the testing framework's answer, they said the leading quote-unquote unit testing framework was such and such. And that just, it made me so sad because it shows right there that not everyone understands that some of these frameworks, like pytest, can be used for more than just unit testing. There is a fundamental difference between testing code and testing features. When we talk about testing code, we mean the actual Python code, or code in whatever language, that we are going to directly call and interact with and make assertions upon. This style of testing is called white box testing. And what we're looking for is to ask, is the code written to do expected things? So for example, if I have a function and it takes in two numbers and the expectation is that it adds the two numbers, I could have a whole bunch of white box tests that would put in different combos of numbers and assert that the sum is what is returned. A lot of times we call these unit tests. Unit tests testing individual functions or methods. We can also have another style of white box testing called a subcutaneous test, where instead of looking at individual units by themselves, maybe it's looking at a chain of calls or a bunch of things together. Overall, though, white box testing is a style of testing that directly interacts with the code. The test can call those functions, methods, and modules directly. On the other hand, there's testing features. And when I say features, I'm not talking about just literal code. I'm talking about the things that we build into our software products. Features are what our end users are going to interact with. End users don't directly interact with code. For example, with web UI apps, they'll be clicking buttons and entering text. They don't have to know anything about JavaScript or Python on the back end. They're just using it like a product or a feature. So when we do what we call black box testing, we are testing the feature, not the code, right? Black box testing doesn't have the code available to call directly. And the goal of black box testing is a little bit different. The question we're asking is, does the product meet the requirements? Does this thing do exactly what I think it should do? Is it delivering that value to the end user? There are many, many kinds of black box tests. Typically, when we refer to integration tests or end-to-end tests or maybe system tests, these are what we would consider black box tests because they're not interacting with the code, they're interacting with the actual feature or product. We need to have a good strategy for deciding when to run different kinds of tests. And that's where the testing pyramid can help us out. The testing pyramid is basically just layering different types of tests in terms of their size and intensity. At the very bottom of the pyramid, we have what we call unit tests. Those are those white box tests that will test things in individual bite-sized pieces. Because unit tests are fast and easy to write, and they're also as close to the code as possible, they're most likely going to catch a lot of issues early if we have good coverage there. So we want to have a lot of good, solid unit tests. They're like the first line of defense. However, unit tests alone aren't good enough because sometimes problems happen when you put things together. And that's where we have our integration and end-to-end tests, those black box tests that we talked about. Integration tests usually mean some sort of service API calls. And end-to-end tests, depending on your application, may mean web tests or terminal app tests or command line tests. But for our purpose, since this is a tutorial on web app test automation, we'll consider web applications to be the main product under test here. The higher up you move the pyramid into integration and end-to-end tests, the tougher things become. The tests are more difficult to write. They have more dependencies. They're more likely to be flaky. The tests themselves are likely to be longer in terms of the number of steps. And they take more time to execute. Consider the rule of ones. Whereas in the industry, a unit test usually takes about a millisecond to run. A service API-based integration test will take about 1 second to run. And an end-to-end web UI test can take about a minute to run. Add that on top of the extra work that a team will need to do in order to implement the automation for the integration and end-to-end tests.
Black box tests like that become very expensive very quickly. And so we don't want to have a bloated suite of tests that we may or may not need at those higher levels. Hence the shape of the pyramid. More testing towards the bottom, fewer tests by number towards the top. We want to mitigate risk while balancing our time and our return on investment. So now let's talk specifically about web UI testing. What is it? Web UI testing is black box testing of a web application through a live browser. During these tests, we will open up Chrome or Firefox or whatever other browser you want to test, navigate to the web page just like you're a regular human user, and interact with things on that page. Web UI testing is feature testing because it tests the app like a user. It is also end-to-end testing because all the parts of a web application are exercised together. Consider all the pieces that make up a modern web app. You have the front end that displays the pages in a browser, consisting of your HTML, your CSS, and your JavaScript all jiving together. Behind that, you most likely also have a service layer, like REST APIs, delivering data to the front end. You'll have a persistence layer, your databases on the back end, whether they're SQL or NoSQL. At the infrastructure, there's also web servers and load balancers. And you may also have queues and workers for heavy jobs that need to go do asynchronous processing or something. So there's a lot that goes into a web application. It's not just the surface level pretty page. It's really like an iceberg. You see just a little bit, but there's a whole ton of weight behind it. There are pros and cons to web UI testing. On the plus side, you do get that nice end-to-end coverage with all those pieces dancing together. The tests also interact with the product mostly like a real user, so you get that sense of coverage. The results are very visible, you can take screenshots, and you're able to catch obvious problems like if you can't log into your app or if an element's missing on the page. However, that comes at a cost. Web UI tests are much more complex to automate than unit tests. As we said, they're slow to execute, which really matters when you get to the size of hundreds or thousands of web UI tests. They're also prone to flakiness because you have to handle race conditions with waiting for the page to load. And finally, root cause analysis is harder than unit tests because you're up at much higher levels, and so you don't always know exactly where the problem is happening. So, what makes a good web UI test? There's a couple pointers I can give. First of all, a good web UI test should focus on one main behavior. Within a web UI application, that could be something like login, or creating a new profile, or uploading a specific document. You don't want a single test to do too many things, because when that test fails, you want to know exactly what the thing that broke was. Furthermore, a good test should have a clear step-by-step procedure. It should be intuitively obvious when you read step-by-step what is going on and what is being covered. Otherwise, triage and root cause analysis could be much, much harder. A good web UI test also covers an important core feature, mostly sticking to a happy path or a basic error case, and trying to avoid rare edge cases or redundant cases or unimportant variations. Remember, web UI tests are expensive to write and expensive to run. And so we want to make sure we're getting the most value out of our tests and we're covering the most important things. It may be worthwhile as part of a risk-based strategy to avoid testing certain things, not because they are not prone to being broken, but rather because we just may not have the capacity to handle that extra amount. We also want to make sure that we're not automating something at a web UI level that could be covered with a unit test or a service test or an integration test. If something could be handled at a lower level, meaning an easier test to write and run and a faster test to execute, we should be automating at those levels instead of at the higher level. Overall, here's a good question to ask ourselves rhetorically. Whenever we write a test, if that test fails, will people panic? And will they know what broke? If the answer is yes and yes, then we have a good candidate for a web UI test, or any test for that matter. Since web UI testing is expensive, focus your efforts on return on investment. Try to get the most out of your tests, whether that means good coverage or covering the most critical parts of your application. Remember, test automation is not a completionist challenge. It should be trying to get as much value as you can. And it's very, very important when it comes to web UI testing. In this tutorial, we will build a test automation solution from the ground up using Python. It's important to remember that test automation is a special domain of software development. Just like we have developers who make web apps or backend services or whatever else could be developed, test automation is a software product, and it needs the same discipline, the same best practices, the same code reviews, tools, stacks, everything that will go into any other domain. So we need to treat it as if it is software development. In our solution, we will use Python as the language for implementation. We will use pytest as our core test framework, the thing that will line up all of our test cases and knock them down like dominoes. For our UI interactions, we'll use a design pattern called the page object pattern to model everything, those clicks, getting the text, all the stuff that you would do to and from a browser. And finally, for the low-level browser automation itself, we will use a package called Selenium WebDriver. Here's what our solution will look like if we were to sketch it out as a diagram. On the left, we will have our test automation code. We will write a series of pytest test cases, and inside of those pytest tests, we will call page object classes, which model higher level interactions like login or searching. Within the page object methods, there will be calls to Selenium WebDriver bindings, which are the low level interactions, the clicks, the scrapes, all that kind of stuff. WebDriver bindings will call out to that intermediate body, which will be like a proxy. If we run our test locally, which we'll do in this tutorial, that proxy will be what we call a WebDriver executable. It'll be a process that will be running on your local machine, and it will serve as a communication way station between your test automation that's running and the live browser. If we were to run tests remotely in a distributed environment, we could use a tool like Selenium Grid, which we'll talk about towards the end of this tutorial. Then, all the way to the right, that WebDriver executable or Selenium Grid will receive requests from the test automation and send them to the browser that's being tested. And all the major browser types are supported: Chrome, Firefox, IE, Safari, Opera, you name it. So, test automation calls proxy, proxy sends commands to browser, browser sends responses back to proxy, which sends it back to test automation. That's pretty much how web UI test automation works. Our tests will specify what interaction should be done, and then it goes off to the browser through our intermediary body. And that's web UI testing in a quick nutshell. Let's pause here and take a brief mental break before we get into the next part of our tutorial. Section 1, setting up pytest with our first test. In this tutorial, we will implement a test automation project from the ground up in Python. And to do that, we are going to take one web UI test case and implement it layer by layer in each one of our tutorial sections. So let's write that basic web test together here. As a best practice, we always want to write our test steps before we touch any code. It's good to be meta like that. We want to make sure that we have a good procedure, apart from whatever code implements it in automation. For our tutorial, the product under test will be the DuckDuckGo search engine. I've chosen to use DuckDuckGo as our product to test for a couple reasons. First of all, everyone knows how to use the search engine. You type in a search phrase, hit enter, and get result links. Secondly, DuckDuckGo is free. Anyone can go to DuckDuckGo.com and use it. And third, DuckDuckGo has a fairly simple interface. It's clean, it's got basic text fields and result links, nothing too crazy, nothing out of the ordinary. So it should be easy for us to write our first test case. The test case that we'll write for our tutorial is a basic search test case. So what we'll do is we will go to the DuckDuckGo homepage, we will enter in a search phrase, and we will verify result links from the result page. Let's step this out step by step so that we all understand the test that we're going to automate. The first step, obviously, is to navigate to DuckDuckGo.com. When we get there, we should see the homepage like this. It should have the logo as well as the search bar. The second step will be to enter a search phrase. We will type it in and either hit the enter key or we'll hit that hourglass logo, or eyeglass logo, excuse me. Then our next steps will all be to verify things on the result page. We should be able to verify the query we entered in the title of the page. We should be able to verify the query in the new search input at the top of the result page. And we should be able to verify that all of the result links somehow pertain to the search phrase. So let's write out our test procedure in plain language. Personally, I like to use a language called Gherkin, which uses these given, when, then steps for writing tests. You don't have to do this, but I like to use the given, when, then format because it helps to frame the setup, the actions, and the verifications, kind of like the arrange, act, assert pattern. So our test case essentially has 5 steps. For our basic DuckDuckGo search, given the DuckDuckGo homepage is displayed, when the user searches for panda, an arbitrary search phrase, then the search result title contains panda, and the search result query is panda, and the search result links pertain to panda. Very basic, very simple. We focused on one key behavior. We have specification by example with our search phrase panda. It's a short, sweet scenario that covers a very, very critical path through the web app. And this is something that if this test fails, then DuckDuckGo has a big problem. So it has good value as a test case, even though it may seem very basic. With our test case in hand, let's put this test into pytest. Pytest is one of the most popular test automation frameworks in Python. In my opinion, it's also one of the best test automation frameworks in any language. Take a look at the pytest homepage here. You can see a very, very simple example of a pytest test case. Test_answer. It's 2 lines. Notice how it's not a class, it's simply a function. And inside this function, we're making an assertion. The assertion is calling a different method or a different function and doing a comparison based on values. This is one of the most beautiful things about pytest. It's so concise. You don't need all this extra gorp to put together a test case. It's very clean, it's functional, it's beautiful. Now, as part of this tutorial, we will use pytest, but I'm not necessarily going to teach pytest. There will be times along the way where I'll point certain things out, like about features or test functions and all that. But if you want to learn more specifically about pytest as a framework, then I recommend reading one of these two books, Python Testing with pytest by Brian Ocken, or PyTest Quick Start Guide by Bruno Oliveira. Both of these books are excellent resources for learning about the pytest framework. Anytime you want to install pytest for your project, it's simply a pip install away. For our project, the one that you cloned from GitHub, pytest should already have been in the pip file. So if you simply do a pipenv install, it should be there. If you want to add pytest to new projects, just do a new pip install for those. If you look at the code in the project that you cloned from GitHub, you'll notice that it already has a dummy pytest test in there. Under the test directory, there's a test module named test_fw.py, and it has a test case that will always pass. Test the tests, assert true. I simply put that in there so you can make sure that your test project works out of the box. If you were to run the pytest command shown here, pipenv run python-m pytest, you should see that it passes out of the box. So let's pause the video here. It's now your chance to do some hands-on coding. Complete section 1 from the README tutorial instructions. It should take you about 5 minutes. As part of section 1's code, you'll add a new test method for that DuckDuckGo search test to pytest, along with its stubs. So give it a try, and then resume, and we'll keep going. Let's take a look at the code for section 1. Here, I have the project open in VS Code, and I have it open to the example branch for section 1. In my tests folder, I've added that test_search py module, and the code is simply one test case function called test basic DuckDuckGo search, and it has each of my test case steps in comments with to-dos to tell me to implement them. And at the bottom, I put an exception just to show that this test case is not ready. And if we try to run it, it'll say, kaboom, incomplete test. I also removed that old test module, test_fw, because we no longer need it. Now, let's run this to see what happens. I've opened up Terminal to my project directory. And so I'm going to run the test by saying pipenv run python-m pytest. -m is the module option. And pytest will discover all the tests in my project and automatically run them. So we can see here, it found one test in tests/test_search py, and it failed. That's that F there. And because it failed, it spilled out all this stuff for trace. We have the test case function, and we have it, and pytest notes exactly where the failure happened. If the test failed because it raised an exception that was not handled, it's this incomplete test. This is exactly what we expect. We wrote our test case first. We've captured the steps in this test function. And even though it's stubbed and it's failing now, this charts the path forward for us to go implement and automate this test case. So this is, even though it failed for now, for us at this stage, this is a good thing. Now let's start implementing some of that automation. Section 2. Setting up Selenium WebDriver. Selenium WebDriver is a free open source package for automating interactions with the live web browser. WebDriver itself is a W3C standard, and the Selenium project is one of its most popular implementations. WebDriver can handle every type of web UI interaction, such as clicking, typing, and scraping text. Many people treat Selenium WebDriver as synonymous with web UI testing. Selenium releases WebDriver packages in many popular programming languages. The lowercase quote-unquote Selenium package is Python's implementation. Its API is very similar to packages for other languages like Java and C#, just with a Python accent. If you ever get stuck on the WebDriver API, check out the Read the Docs page here. You might be wondering what browser type Selenium WebDriver can handle. The good news is that Selenium supports all major browsers on all major operating systems. That includes Chrome, Firefox, Safari, Internet Explorer, Edge, and Opera. Just be warned that each browser has its own quirks, so you might need to write certain automated calls differently depending upon the target browser. Selenium WebDriver by itself is just a programming package. It needs that proxy server or that intermediary body that we talked about before to communicate with live browsers. For example, it needs Chrome Driver to work with Chrome. Here's the page for Chrome Driver. Other browsers need other kinds of drivers. For example, Firefox needs one called Gecko Driver. These extra drivers can be downloaded from their project pages. You will need to install them onto the system path of your test machine. Many people overlook this step when they first set up a new test automation solution, and they don't know why their web UI tests won't open the browser. If you need help installing these drivers, please follow the README instructions from our GitHub project. You should have already installed them by this point in our tutorial. As a warning though, be wary of browser versions. Browser vendors frequently release updates, and version incompatibilities between browsers and drivers can break tests. Believe me, I've been burned a few times before. Just make sure to stay on top of updates. Before jumping back into the code, there's one more thing we should discuss about WebDriver. Every test case should have its own WebDriver instance. Each test should initialize a fresh WebDriver instance as part of setup, and it should quit the instance as part of cleanup, no matter what. Why is this so important? Test cases should be independent from each other. That means no test case should share any resources or dependencies with another. Otherwise, problems in one test case could impact others. Sharing a WebDriver instance might seem like a nifty way to gain efficiency, but it's dangerous. Plus, tests that share WebDriver instances can't easily be run in parallel either. Quitting the WebDriver at the end of the test is also crucial. Without explicit quits, WebDrivers and browsers might become zombie processes. Make sure WebDriver instances get quit no matter what, regardless of any features or exceptions. Let's make sure that our machine is ready to do some Selenium WebDriver testing. I've already installed Chrome Driver and Gecko Driver on my system path, but I'm going to run those commands here just to make sure it works. So Chrome Driver works, and looks like Gecko Driver works as well. Great. Oops. Next, I'm going to install the Selenium package. pipenv install Selenium. It might take a minute, but it should work just fine. Great. Let's get into the code. All right, into the code we go. Typically, test frameworks have setup and cleanup methods for handling things like initializing and quitting Selenium WebDriver. In pytest, we use what we call fixtures. Here, I have under my tests folder a module called conftest.py. This module contains all the fixtures for our project. In here, I have a function decorated with @pytest.fixture. And inside of this is where I'm going to do my WebDriver setup and cleanup. Note that we'll need to import the pytest and selenium.webdriver modules. The fixture has 4 lines. First, I'm initializing my WebDriver instance. I say selenium.webdriver.chrome for Chrome, and I'm storing that in a reference object. This will initialize the Chrome driver instance. It'll send a command to my local machine, look up Chrome driver on the path, and start that execution automatically. The second line is setting an implicit wait time for 10 seconds. This means that every time we try to find an element on the page with this particular WebDriver instance, the WebDriver will smartly wait up to 10 seconds for that element to appear, rather than dying right away if it can't find it. We'll talk a little bit more about waits later in the tutorial. The third line is a yield, and that returns the WebDriver instance for this particular browser, or for this particular fixture. Now, if you're familiar with Python, you may recognize yield as a keyword. Yield means that this function is actually a generator. It gives a sequence of elements. When it comes to fixtures in pytest, fixtures can be generators. Everything that happens before the yield statement is part of the quote-unquote setup phase of the fixture. And returning a reference to something will return that object to the test case that calls this fixture. All this will happen before a test case executes. Then, everything that happens after the yield statement in a pytest fixture is what we consider part of the cleanup routine. This will be called automatically after the function executes, no matter what happens in the function, even if it raises an unhandled exception. So, after the yield statement here, I enter the cleanup phase, and what do I want to do when I clean up a WebDriver? I want to call quit to kill that WebDriver instance. Note that I want to use quit and not close because they mean 2 different things. We also need to update our test case function. So go over to test_search.py, and you'll see our stub test function here. The only change we need to make in order to call this fixture is to add the fixture's name as an argument for the test function. This is a pytest trick. Whenever pytest sees a test case with a fixture name, it will look for fixtures either within the same test module or within a file named conftest.py, and it will match based upon name. So since our fixture name was browser, and this argument name is browser, when pytest runs this test case, it knows to call the browser fixture before this test case runs, and then the second iteration of the generator after this test case completes. So that's how we can use fixtures for WebDriver setup and cleanup in pytest. Now it's your turn to play. Complete section 2 from the README tutorial instructions. It should only take about 5 minutes. Pause the video here until it's done. So, let's run our test case now that we have our fixture implemented. What should happen is that pytest will discover the test, call the fixture, initialize WebDriver, and we should see Chrome flicker up on the screen. And then it should shut down very, very quickly because there's nothing that's actually happening in our test case. Furthermore, the test case should still fail like it did the last time. Let's see if that happens. So pipenv run python-m pytest. Let's go. And boom, whoa. So we saw the Chrome window come up and down, and we're still failing for the same reason. So we know that our fixture was successful. It's doing exactly what it was supposed to do, and that itself didn't have any problems. Let's move on to section 3, defining page objects. A page object is an object representing a web page or a component. There are two main parts to a page object. It has locators for finding elements on a page, and it has interaction methods that interact with the page under test. Each web page or component under test should have a page object class. Page objects encapsulate low-level Selenium WebDriver calls. So that way, tests can make short, readable calls instead of complicated ones. It helps to maximize code reuse. Our test case interacts with two different pages. The first page it interacts with is the search page. And there are really two interactions it does. The test will load the search page, and it will search for a phrase on the search page. For the result page, there are technically three interactions, even though it's not necessarily doing something on the page to enact change. Instead, the test is getting three values, which in a sense is still a web UI interaction. The three things that the test will get off of the results page are the result link titles, the search input value, and the title. Let's look at the code to see how these page objects can be stubbed out. In our project, I created a new folder called Pages from the root level directory. Note that the Pages directory is not inside the tests directory. They're two separate things. I added a dunder init.py module to say that, hey, Pages is going to be a package. That way we can import it anywhere within our project, namely by the tests. Let's take a look at the search page. So I created a module called search.py, and in here I've created a class called DuckDuckGo search page. There's an init method that will take in a reference to the browser, which is the WebDriver instance that'll come from the test case, and it stores a reference to it internally. I've also created two stubbed methods, one for loading the page and one for searching the page. Loading the page doesn't need any inputs, but searching the page requires the search phrase. For both of them, I've left a #todo comment as well as the no-op pass command. The result page will have a similar format. Again, I have a class named DuckDuckGo result page, and likewise it has the dunder init method. The three things I need to get from the result page each have their own method: the result link titles, search input value, and title. However, instead of having the pass command, each one of these returns a value, because that's the point of these interactions. They're supposed to get something and give it back. So for my titles, I'm going to return an empty list for now. And for my search input value and my title, since those are strings, I'm going to return an empty string temporarily. With our page object classes stubbed out, we can actually implement the test case function. Let's open it up. testsearch.py. Here's my test case function. Notice how I've added these import statements from my pages package, import the two page object classes. In my test case at the top, I'm going to initialize each of those page object classes. I've also moved my search phrase to be a variable, just to make it a little easier to reference. Each of my steps can now be implemented using page object calls. So my first step, given the DuckDuckGo homepage is displayed, I want to say search page load. When the user searches for phrase, search page search for my phrase. my 3 assertion steps. Then the search result title contains panda. Assert that the phrase is in my result page title. And the search result query is panda. Assert that my phrase equals result page search input value. And finally, the more complicated one. And the search result links pertain to panda. What I need to do for this is get all the titles from my result page result link titles. And I'm using this list comprehension here to see how many matches I have for my titles for my lowercase phrase. And I want to make sure that I have at least one. It may not be the most robust or strongest assertion, but given how search results can vary and they can change, I think for the case of a basic search test case, making sure that at least one of them was right is good enough for the purposes of this test. We could have other tests to do more in-depth searching and querying and stuff. We just want to make sure that here we get something decently good on the page. I'm still going to keep my exception at the bottom because even though we have implemented all the code for this test case function, the test case is not still automated yet because these methods are effectively still empty. They're only stubs. Nevertheless, what we've done is actually pretty powerful. Even though we haven't even done any direct WebDriver calls yet, we have been able to sketch out the entirety of this WebUI test case, just based on the interfaces of the page objects alone. Like I said before, always think before you code. And in this case, we're taking a top-down layer-by-layer approach. We had our test case, we put it in pytest, we stubbed out each of the steps with to-dos, and then the next layer down, we stubbed out the page objects and implemented the steps in our test case. So in future lessons, we'll continue going down layer by layer until we've automated this whole thing. So now it's back to you. Pause the video here and complete section 3 from the README tutorial instructions. It should take you no more than about 10 minutes. Then, after you've added your page object code, run the test again and make sure it fails in the same way to show that you haven't broken anything. So let's run our test. We should see Chrome flicker up and down, and we see the failure here. Now, even though it fails in the same way that the test case does fail, the reason for the failure is actually a bit different. If you notice here in the trace left by pytest, it fails on the first then assertion. Assertion error. Assertion panda is in the empty string. Remember, we stubbed the title method. This title method is only going to return the empty string. Yet our assertion, once the test case is fully implemented, is expecting our search phrase panda to be in that title. So naturally, the test at this current state would fail here. This is to be expected. Let's move on to section 4, finding locators for elements. A web element is a thing on a web page. Things like buttons, labels, text inputs are all what we call elements. In fact, everything you visually see on the page must be a web element. Tests interact with elements in 3 steps. First, the test must wait for the target element to appear on the page. Think about when you log in somewhere and you're waiting for it to load. It might take a little bit for those elements to pop and appear. That's the first step, waiting for that element to appear. You can't interact with an element that doesn't exist yet. The second step for interaction is to get an object representing the target element. What we'll do with our automation is we'll use a find call to say find an element given some query, some locator. And then if the automation is successful at doing that, you'll get back a web element object that represents that element that was discovered. The third part to an interaction is that we will send commands to that element object. It may be something that should enact change on the page, such as clicking an element. Or it may be that we want to get properties from the element, like its text value, or maybe some HTML attribute value. All these things are part of an interaction with an element. As humans, we don't think twice about it. We go to a page and we just click it or type it or whatever. But we need to handle these carefully with test automation so that they're done right. When we try to get an element on a web page, we need to use what's called a locator. A locator is a query that finds an element on a page. There are many, many types of locators. We can find elements by their ID attributes. We can find them by their name attributes. Maybe we can find them by their CSS class name, or even by a full CSS selector. If all else fails, we can always find an element uniquely by an XPath, even if that's a little bit complicated. Furthermore, with Selenium, we can also select elements by their link text, by partial link text, or by their tag name. Let's look at some element locator examples together. Here's a very simple one for an ID locator. If we have, let's say, a button element with an ID attribute value of Django_OK, because it has this ID attribute, we can use the ID locator type. My locator type is going to be essentially a tuple. It's going to be whatever my type is by .id, which is a Selenium value. And then it's going to have the query portion of that locator, which in this case is the ID value, Django_OK. ID locators are really, really nice because IDs for elements are supposed to be unique on a web page. So this is just a single one key value to get exactly what we want. Now, I always recommend, even if you see an ID in a web element, check the entire page just to make sure it is truly unique, because just because something should be one way doesn't mean it actually is. But if you are fortunate enough to get an ID, I recommend using this. However, not all elements have IDs, and so we may need to use other kinds of locators. CSS selectors are a more powerful locator type than IDs, because with CSS expressions, you can cover many more kinds of elements. Let's consider our button element again, but instead of having an ID attribute, let's say it has a class attribute. We could easily write a CSS selector locator using CSS syntax, button.django_OK. The nice thing about CSS selectors is that they support anything in the CSS language. So if you're familiar with CSS, you can just drop your CSS knowledge here like it's hot. Now, let's look at a more challenging example. What if our button element does not have any attributes on it? In this case, we'll need to use an XPath to uniquely identify this element. XPaths can uniquely identify any elements on a page. They can use text and indexing to make that happen. So here, with my XPath locator, I'm using this query here. The double slashes indicate that I want to search from the root element down to any sub-elements. Button is the tag name for the element. The square brackets denote conditions. And within my condition, I'm going to use the text function to get the textual value of my element. And I want to select every button in which the text equals the string OK. This is a very, very simple XPath. Sometimes XPaths can get really, really long and really hairy. But XPath is a standard. So if you want to learn more about XPath, you can simply look it up online to learn the syntax. Our test case needs to locate 3 different elements on the DuckDuckGo website. It needs to find the search input on the search page, the search input on the result page, and the result links on the result page. Now you may be wondering, what about the title of the result page? The title is actually not an element on the page. The title is an attribute of the page. So we'll need to get that using a slightly different WebDriver call. Finding locators for elements can be pretty challenging. It's one thing to know the different types of locators and to know how to form queries when you already kind of know what the attributes are, but how do we find elements and figure out what those attributes are on a live page? Thankfully, Chrome developer tools can help us out. I like to use Chrome DevTools because I think it's easy and it's what I'm used to, and Chrome is one of the most popular browsers out there in the market. So let's go to DuckDuckGo's homepage and I'll show you how I can get the search input on the search page. If you right-click anywhere on the page in Chrome and you go to Inspect, you'll open up Chrome's developer tools and you'll see it over here on the side. Now it's really cool. As you saw me hovering over different elements on the page in the source code, you'll see that Chrome will highlight that element visually on the actual web page itself. You can also come up here to this upper right icon with the cursor, click it, it'll turn blue, and then you can scroll or you can hover over anything visually on the page and it will link to the source code highlighting as well. So I want this search input, so I'm going to click it. You can see that's here. This input element is the input I want. Notice how it also has an ID. The ID is Search Form Input Homepage. I'm going to search that page here just to make sure it's unique on the whole page. I'm going to use the CSS selector with the hashtag, which will search for ID. And we can see 1 of 1. This is unique on the page. So I can use this ID value. Once we've identified our locator, we can put it into our page object code. So I've got the code open here again, and I'm in my pages search.py module. The class should look familiar, and it's still stubbed out. But now here, as class level attributes, I'm going to add my search input locator. I'm using all caps to denote that this is a class level attribute. And I'm coding my locator as a tuple. That's with the parentheses. I'm using by ID as my type, and that by class comes from the Selenium WebDriver common by module, which I've imported here. So my locator is the ID type. That'll be the first part of my tuple. And the second part of my tuple is that ID value that I got from inspecting using Chrome DevTools. In the next section, we'll use this locator with our WebDriver calls in the methods below. So now it's your turn to give this a try. Complete section 4 or the README tutorial instructions. What I recommend you do for the result page is try to use Chrome DevTools on your own to try to find locators before you look them up in the example code. This should take you about 15 minutes. So pause your video and hop to it. So once you've completed the code for this section, your result page object should look like this now. You should have 2 more locators, result links and search input, and they should be like this. Maybe you found something a little bit different when you inspected the page, but this is just what I have when I found it. So this is what I put in my example code. There's more that I can say about web element locators than I could possibly fit into this tutorial. If you want to learn more about how to write good web element locators, hop over to Test Automation University. There, I've created a course called Web Element Locator Strategies, right here. In this course, I cover all the different types with all different kinds of strategies for how to write good locators. If you want to write more tests for Web UI and more robust tests, I highly recommend taking this course. There's another course on TAU that might interest you as well. If you want to learn how to apply artificial intelligence and machine learning towards identifying locators for web elements, check out this course here by Jason Arbin, AI for Element Selection. It's a short course, but it'll really expand your mind. Let's move on to Section 5, making WebDriver calls. WebDriver can handle any type of interaction with a web page. However, it is a complex API. Thankfully, it's very similar between different programming languages. If you ever get stuck, I recommend reading the docs online. Frequently, I refer to this page myself. To make things a little more understandable, let's go through some of the most common calls together before we try to apply them to our test automation project. The left column shows calls directly from the WebDriver instance, which we named browser in our code. Current URL returns the URL of the page currently loaded in the browser. Find element returns an object representing the first element found by a locator. If no element is found, then this method throws an exception. Find elements, plural, returns a list of element objects found by a locator. If no elements are found, instead of throwing an exception, this method returns an empty list. The Python WebDriver also includes a findElementBy method for each locator type. Typically, I don't use these methods because I prefer to use two-part locator tuples, but many people prefer the shorter syntax. The get method loads a given URL in the browser. Maximize window maximizes the browser's window size. Quit closes the browser and terminates the process. Refresh refreshes the current page. Save screenshot will capture the current browser window and save it to an image file. And title returns the page's title. The right column shows calls for element objects returned by the findElement methods. Clear removes all text from a text field. Click clicks an element. FindElement methods will locate elements starting with the current element as the root. GetAttribute returns the value of an HTML attribute, and GetProperty returns the value of an HTML property. IsDisplayed returns true if the element visually appears on the page and isn't hidden, and it returns false otherwise. Location returns the X and Y pixel coordinates of the element. SendKeys sends keystrokes to the element to simulate the user typing. Size returns the pixel dimensions of the element. And finally, text returns the text value of the element. The best way to learn the WebDriver API is simply to get your hands dirty with code. What we'll do is I'll show you the code for my page objects with the WebDriver calls. We should always try to put our WebDriver calls inside of page objects so that test cases will call page objects instead of Selenium WebDriver calls directly. So in my project, back in my pages package, I've got the search.py module open, and we'll see that it's now implemented. I've got not only the init method I had before and the locator I had before, but now the methods have implemented bodies. Let's look at the load method first. So the load method is supposed to load the DuckDuckGo search page. In order to do that, I need to use the browser get method, and I need to pass in the target URL. So I say self.browser, because that was the browser reference passed in, get to load the page, and then self.url to pass in the URL. I've set the URL as a class attribute here, https://www.duckduckgo.com. That's all this method needs. The search method is a bit more interesting, because the search method needs to do a web element interaction. So first what I need to do is I need to get that web element. And I'm going to use the self.browser.findElement method. As you recall, the findElement method will return an element object representing the element as found by our locator. The locator I want to use is this search input locator that we implemented in the last section. So I'm going to pass that into this findElement method. And if you notice, there's this asterisk operator in front of it. The findElement method requires two arguments, the locator type and the locator query. But since I've stored my locators as tuples, I need to do an argument expansion on my tuple so that each of these elements in my tuple will get substituted positionally for the arguments in this method. That's what the asterisk operator does in Python. It is an argument expansion operator. So that way I can declaratively implement my locators as readable tuples and simply pass them around by reference using argument expansion. If this call is successful, then it will return my element object. And I want to store that in a variable called search input. If you recall from our fixture, we had that implicit wait for 10 seconds. That means that the browser will implicitly wait up to 10 seconds for this element to appear instead of choking if it doesn't find it right away. So that's a good thing. Once we have our element, we can finally send commands to it. So if I want to type a search phrase, I need to say search input dot send keys, because that simulates the keystrokes of a user. And the keys I want to give in are the search phrase. And then I also want to add on the return key, because that will simulate the user hitting the enter to commit the search to be searched. This keys class comes from the Selenium WebDriver Common Keys module. And that's all there is to implementing our search page. Let's take a look at our result page next. So result page will be similar to search page. We already had our locators. We already had our init method. And now we have new interaction methods implemented. The result link titles will need to use the results links locator. And if you notice here, instead of saying browser.findElement singular, it's saying browser.findElements plural. The reason is because there will be multiple result links on the result page, and I want to get all of them. So I use the plural form of getElements, and I store that into an object called links. Now, links represents a list of element objects. I don't want to return the element objects themselves. Instead, I want to return the title strings for the element objects, because I can make assertions on the title strings. So what I'll do is I'll do a very simple list comprehension. I'll say my titles is equal to a list of link.text for all of my links in the links list. This is essentially a mapping. It's saying map from your elements to those elements' titles. And so this list will be a list of strings of all the titles from all the links. And the titles come from the getText attribute. Finally, I have my list of titles. and I'll just return it. The search input value method is another element lookup method. So for this one, what I want to do is I want to go to the search input and I want to get whatever text has been entered into that field. So I'll use self.browser.findElement, singular, because there's only one on the page. I'll pass in my search input locator, and I'll store that in my element object. Now, you may think that because I'm trying to get the text out of this element, I can use the .text attribute like I did for my links. However, this search input is a bit special because it's not just any type of HTML element. It is an input element. And if you do .text on an input element, you'll actually get the empty string. And this may be confusing and unintuitive, but within HTML is actually correct. In order to get the value entered into an input field, we need to get the attribute named value. So here, once we have that search input, we're going to say search input get attribute value to get the textual value of that input field. And then we'll return that. It's a little bit confusing when you're new to Selenium, and this has certainly burned me a time or two. So just watch out for it. Oops. The third and final method to implement in the result class is the title method. Now, as I said in a previous section, the page title is actually not an element on the page, but rather an attribute of the page. So instead of trying to find an element for the title and get text off of it, the title attribute with the Selenium driver API actually comes directly from the WebDriver instance. So for the title, we say return browser.title. So that was a lot of words and explaining for what seems like just a little bit of code. But I hope that stepping through each of these page object methods helps to make sense of the WebDriver API and how we should be calling it. So let's pause again for y'all to take a chance to do some coding. Complete section 5 from the README tutorial instructions. You'll be adding those WebDriver calls to your page object stubs. Once you add them, also try to run the test, because now the test should be completely implemented and it should run successfully. Let's run the test to make sure it works. At this point, the test is fully implemented. So when we run it, we should see the pytest banner load. We should see the Chrome window open up, the search phrase entered, the results page appear, Chrome closed down, and a green passing result. Let's give it a try. So my hands are off the mouse and keyboard at this point. And we see Chrome, search phrase, result page, close, pass, done. Nice. Our test is working. If for some reason your local code isn't working, there's a few things I can recommend to check. First of all, make sure that WebDriver is correctly installed. Chrome driver should be on your path, and the versions for Chrome as well as Chrome driver should be the latest and greatest. Secondly, double check your Python code. Make sure it looks like what we see in the example code. If you have any typos or you did something differently, then your test may not work like mine did. Our basic test automation project is working, and that's great news. So let's plus it. Section 6, configuring multiple browsers. As we said before, Selenium WebDriver is compatible with all major browsers on all major operating systems. When it comes to our test strategy, it's up to us to determine what browsers we should or should not be testing. We should look at things like market share and our user base to make the best decision possible. No matter what though, our web UI tests that we write should be able to easily run on multiple browser types. Furthermore, headless browsers are great for test automation. A headless browser runs web pages but does not visually render them on the screen. This makes headless browsers run more efficiently. Both Chrome and Firefox have headless modes. Typically, I use non-headless mode when developing automated tests and headless mode when running tests in a continuous integration system. Browser or headless mode aren't the only choices test automation needs. Tests usually need inputs like URLs, usernames, passwords, and even default timeout values. Inputs need to be passed into the automation when a test suite starts to run. They should not be hard-coded into the automation code, especially if they are sensitive values like passwords. They should be handled separately so that their values can easily be changed for different test suites, and also so that secrets aren't committed to source control. There are a couple of ways to pass inputs into test automation. Arguably, the easiest way is to use a text-based config file. Config files can come in many formats, like JSON, YAML, INI, or CSV. They simply have a bunch of different values in them that can be read in and parsed using standard modules. The reason to use a text-based format instead of a different kind of format, for example, like Excel, is that text-based formats are easy to diff when it comes to code reviews. You could also use encrypted files, which might be a little bit safer, but a little bit tougher to deal with. Instead of files, you could also try to pass inputs into automation using environment variables. You could use Python's OS module to read environment variables directly. However, environment variable inputs are limited to being one-dimensional strings, and they could also change easily based on the system under test. A more robust and serious solution would be to use a key management service, like AWS KMS or Azure Key Vault. Key managers store secrets in safe places. Automation can make authenticated calls to retrieve the secrets. However, for smaller automation projects, this might be overkill. You might be wondering if pytest can just take in parameters at the command line. Although pytest has several helpful command line options, unfortunately, it can't take custom arguments. So trying to pass custom arguments into pytest through the command line is a showstopper. You need to fall back on one of the other strategies. In my opinion, I think JSON config files are the easiest solution. As a file format, JSON is readable and hierarchical. And from a coding aspect, the JSON module is part of Python's standard library. With one line of Python code, you can read in a JSON file into a Python dictionary and reference it by key name. It's super easy and super simple. Let's see how we can use a JSON-based config file to read inputs into our test automation project. I have the code open here again, and I've created a file called config.json. It is in the root level of our project directory, and it's a JSON object with two values. I've created a value named browser, which will take the desired browser name, and I've also added one called implicit weight. This will set that implicit weight field on our WebDriver instance. It's good to have that parameterized because when we try to run against different environments, we may need to tune that weight value to be appropriate. The best way to read this config file is to create a fixture in conftest.py alongside our browser fixture to read it. So let's go to conftest.py. Here, I've added a new config fixture. We created it just like we did our browser fixture. However, for my config fixture, I've set the scope to be session. I want the scope to be session so that this fixture is called one time for the entire test suite run. there's no need to reread the same config file for every single test run, because that's inefficient. I can read it once and be done. It's also safer this way, because if there's a bad actor that tries to change that config file's values in the middle of the run, that could cause some problems with the test automation. So if we read it in once and leave it, then it will be the same for every single test in the suite. Our config fixture has a few different parts. First thing we need to do is read that config file. And there's nothing magical about this. This is just plain old Python code. So with open our config file path as a config file pointer, my config object is going to be json.load config file. The load method comes from the JSON module, which I've imported here. One line, you can read that JSON file into a dictionary. The second part of my config fixture is that I want to make sure that the values in my config file are acceptable. It would be really stinky if we put in a bad browser name or had a typo and it caused every single test to fail. So let's catch that before anything happens. And if there is a problem, we can abort right away and save ourselves some time and hassle. So I want to make sure that the browser value in the config is one of my supported browser types: Firefox, Chrome, or headless Chrome. I also want to make sure that my implicit weight value is an integer that is greater than 0. If these assertions all pass, then I know my config is good, and I can return that config object so that other test cases and fixtures can use it. Finally, I'll need to update our browser fixture as well, because the browser fixture is what initializes the WebDriver, and the browser choice comes from the config. So down here, I have my browser fixture, and notice how it's declaring config as a dependency. What pytest will do is every time it sees the browser fixture, it will call the config fixture. So this config input will be dependency injected into this browser fixture, just as if it were a test case. That's really cool. Let's see the changes we had to make in our browser. So where we used to have a one-line call to initialize the WebDriver for Chrome, now we have to make a selection. We have to make a selection based upon the config's browser value. If it's Firefox, we'll set Firefox. If it's Chrome, we'll set Chrome. And if it's headless Chrome, we need to use Chrome options to add the headless arguments to browser initialization. And I'll pass in those options when I initialize the Chrome WebDriver. If none of those are found, raise an exception because that's not cool. The other three parts of our fixture are pretty much the same. The only difference is for my implicitly wait call, I need to pass in the implicit wait value from the config. Otherwise, it's the same. We don't need to change the test case itself in test search. The test case will still get the browser dependency injected from the fixture. It's just now that there's extra magic happening within the browser fixture by calling the config. The test case itself and the page objects do not need any code changes. That shows a good separation of concerns within our test automation framework. With our config changes in place, let's now run our test on headless Chrome. I've already set headless Chrome in the config.json file, as you saw. So when we go to run our test, this time we should see pytest run, but we shouldn't see the Chrome window pop up because it should be in headless mode. Let's give it a try. So there it goes. Chrome hasn't appeared yet. And boom, the test case passed. And it took a little bit less time than when Chrome was running without headless mode. That's pretty cool. There are other ways you could handle browser choice. One way you might ask is, why not parameterize browser choice using pytest mark parameterize? You could do it that way, but I advise against it. And the reason why is because browser choice is an aspect of testing. It's not a test case value or necessarily a test case variation that you want to tightly control. But rather, it's an aspect of testing in that, in theory, every test should run on every supported browser. Furthermore, from an implementation standpoint, if you were to parameterize every test case with different browser options, that would create a ton of duplicative code. When you use something like a config file or another input mechanism, every test case run will target one specific browser. And if you want to run multiple browsers, you simply launch multiple test suite runs with different input values. So you're saving yourself code and you're saving yourself hassle. Let's pause here so you can have a chance to try to run on Chrome and headless Chrome using config inputs. Complete section 6 from the README tutorial instructions. It should take you about 15 minutes. Once you get all the code changes in, try running all three browsers: Chrome, headless Chrome, and Firefox. Let's see what happens. So I showed running with Chrome and with headless Chrome. Now I'm going to show Firefox. It should work the same, but we should always make sure. So we see Firefox coming up, and it's going to search. But for some reason, what? It failed. That doesn't make any sense. The code's the same, it's the same test procedure, but simply running it on a different browser made it break. That's not good, and we'll figure out why in the next section. Section 7, handling race conditions. A race condition happens when actors access the same resource at the same time without following an order of operations. Race conditions are notorious for causing flakiness in any type of black box testing, but especially for web UI testing. With web UI testing, race conditions can happen whenever automation attempts to interact with an element on a page or an attribute of a page before it is ready. To mitigate this race condition, we should always wait for the thing on the page to be ready, whether that's an element to appear or a property to change. There are two kinds of waiting that we can do. We can do implicit waiting or explicit waiting. Implicit waits are specified once and applied to all interactions. Our solution has an implicit wait that we set when we initialized the WebDriver instance. Implicit waits are good for small projects where there's not too many interactions going on, or where most interactions will roughly take the same amount of time. Explicit waits, on the other hand, must be specified for each interaction. They are more complicated to implement, and you need to implement them, as I said, for every single interaction. However, they do give you a much better grip of control over what is being waited for. As a warning, don't mix implicit and explicit waits. Your solution must use one way or the other. And that comes directly as recommended by the Selenium project itself. If you try to mix your implicit and explicit waits, you'll probably end up with some unorthodox behavior. If you want to learn more about the different kinds of waits, I strongly recommend reading the Read the Docs page for Python Selenium WebDriver. They have a whole page on waits where they have examples of explicit waits, expected conditions, custom wait conditions, and implicit weights. Let's take a second look at our test case failure from before. This failure is due to a race condition, but let's see why. If we look at the trace from the pytest test case, we'll see that the assertion that failed is this one. Assert that my phrase is in result page title. And the assertion with its substitution values says assert panda in DuckDuckGo privacy simplified. That means that this assertion was trying to verify that phrase being panda should appear in DuckDuckGo privacy simplified being the value of the result page title. We know that the test case should have, by this point, changed over to the result page and therefore updated the title. But that hasn't happened. This clearly is the title from the search page, which means the race condition here is that the automation executed this assertion before the result page title was ready and had flipped over. Clearly, Chrome changes titles faster than Firefox. That is an unusual and peculiar difference between browsers, but these things can happen. There are a few ways we could try to fix this race condition in our code. One way would be to introduce a hard sleep. I could add a hard sleep to make the automation wait for 5 seconds before checking the title. However, we should never, ever add hard sleeps or hard waits to our automation. They make our tests take much more time than necessary. And even if we add some delay time, there's still a race condition here, right? There's still the actors competing between the automation waiting and the page loading. So hard sleeps are almost always a poor solution. Another solution would be to add an explicit wait here. We could make it explicitly wait for the title to change. However, for our small solution, that's not entirely practical. We would have to then undo our implicit wait and update every other interaction to have an explicit wait. That's cumbersome and painful and beyond the scope of this tutorial. Thankfully, there is a third way that may seem like a bit of a cop-out, but it still gets the job done. This is the only assertion that is not working with a web element. These two assertions work with web elements. The implicit wait that we put on our WebDriver applies to web elements, but not to attributes of the WebDriver. If we simply reorder our steps to make the title check happen last, then it forces the implicit wait to happen here on the page to load. And by the time the test would get down to this step, the title would have definitely changed. So let's give this a try and see what happens. Let's give our updated test case a try. Rerun. Firefox is coming up. And this time it passed. Very nice. So give this a try for yourself. Pause here and complete section 7 from the README tutorial instructions. It should take you about 10 minutes. Once you make the code change, run it in all 3 browsers, Chrome, Headless Chrome, and Firefox, and make sure that all 3 work. Let's move on to section 8, running tests in parallel. Unfortunately, web UI tests are slow. Compared to unit tests, which take a fraction of a second, web UI tests could potentially take up to minutes to run. This may not seem like a big deal with our current test solution because we only have one test and it is very fast. But in the industry, it's very, very typical for the average web UI test to take about 1 minute to execute. And that's 1 minute per test. I would say, based on what I've seen, the range is between 30 seconds and a minute and a half, usually. And it depends on environmental factors and the performance of the application under test, but 1 minute is a fairly reasonable benchmark. Think about if you have a test suite with 100 tests. That would take 1 hour and 40 minutes to run if each one takes a minute. Now imagine if you have a test suite with 1,000 tests. That will literally take almost all day. It'll be about 17 hours. And for large web applications, 1,000 tests really isn't that large of a test suite, to be honest. So we need a way that we can speed up our tests if we're going to effectively test our application with automation. For the sake of demonstration, we can inflict a bit of this pain on ourselves easily. Let's go to our test case and let's parameterize it with multiple inputs. On our test function, I've added pytest mark parameterized from the pytest module. And I'm setting the phrase to be panda, python, and polar bear. This list will make this test case run 3 times, once for each input. And the phrase will be passed in as an argument here. So rather than setting my phrase in my test function, I'm getting it from the parameter values. Now let's run these tests. We've multiplied them from 1 to 3, and they should take longer. First one is done. Second one is done. And third one is done. In total, these 3 tests took 14 seconds, which by industry standards is actually pretty good. But I'm sure it felt painful to sit there and wait for those tests to complete, even as they were running in headless Chrome. The best way to speed up web UI tests is to run them in parallel. Now, running tests in parallel is not always as easy as flipping on a switch. But if you've built your test solution with good principles, it shouldn't be too difficult. With pytest, we can install the pytest xdist plugin with a pip install call to enable us to run test cases in parallel. Pytest xdist not only lets us run in parallel on our local machine, but it also enables us to distribute tests to multiple machines. Next, we need to make sure that our test cases are truly independent. They cannot have any collisions in which tests will be accessing shared state. That goes for collisions within the automation code, meaning like no global variables or static variables or anything, but also collisions in the product and features under test, right? If you have 2 tests in parallel hitting the same database, in theory, those tests could undo each other. So you need to make sure you avoid collisions like that. And finally, you need to make sure that each individual test has good performance in and of itself. Right? We can parallelize till the cows come home. But if individual test cases are taking 5 minutes, 8 minutes, 12 minutes, speeding them up in parallel is only going to do so much. Right? Each individual test needs to be performant in its own right, meaning no hard sleeps, smart waits, perhaps using REST API calls to seed data rather than use the WebI to seed data, techniques like that. So let's use pytest xdist to run these tests in parallel. I've already done my pipenv install for pytest xdist, so I'll just run the test here. We'll use the same pytest invocation command, but now we're going to add the -n option. The -n option allows you to specify how many threads you'd like to run. I'm going to run with 3 threads. The banner looks a bit different. But as you can see, they ran much more quickly. We had the 3 tests execute in only 9 seconds, down from 14 seconds. So give this a try. Complete section 8 from the README tutorial instructions. Should take you about 10 minutes. Install pytest xdist, try to run the tests in parallel, and make sure you try each of the browsers as well to make sure we're still compatible. Before we end this section, I want to share even more information about running tests in parallel. Running tests on one machine is convenient, but it doesn't scale well for large-scale parallel testing. That's where Selenium Grid can help. Selenium Grid is a free, open-source tool from the Selenium project for running remote WebDriver sessions. A grid has one hub that receives all requests and multiple nodes with different browsers, operating systems, and versions. Automation can request a session with specific criteria from the hub, and the hub will allocate an available session from its nodes. Selenium Grid enables not only parallel testing, but also multi-config testing. For example, tests can run from a Windows machine, could request sessions for Safari on a Mac OS machine. There are also 2 ways to use Selenium Grid. You can set up your own instance and manage the infrastructure yourself, or you can pay for it as a service. Several companies like Sauce Labs, Lambda Test, BrowserStack, SmartBear's cross-browser testing, and others all provide cloud-based WebDriver sessions with extra features like logging, videos, and test reports. These services can be a great solution if your team needs to test multiple configurations or doesn't want to spend resources on infrastructure. If you want to learn how to set up your own Selenium Grid instance with Docker, check out this Test Automation University course entitled Scaling Tests with Docker. Carlos Kidman does a great job showing how to quickly spin up Docker containers to build Selenium grids with any number of nodes. If you want to learn more about parallel testing, check out my article, To Infinity and Beyond, A Guide to Parallel Testing, on automationpanda.com. That article goes into detail about prepping your tests for parallel testing and different ways to scale. Let's do our final section, the bonus section, adding more tests. At this point, you have finished the guided part of this tutorial. Congratulations! I hope you've learned quite a bit. But that doesn't mean that our learning is over. Practice makes perfect after all. And we have a Python test automation project that can serve as the basis for more tests. So, what I'd like for y'all to do is to try to add more tests on your own to your project. I've listed some ideas for tests that should be easy based on the basic search tests we've already done for DuckDuckGo. You can continue to write DuckDuckGo tests, such as search by clicking the button instead of typing return, or clicking a search result, maybe expanding more results or doing different types of searches or even changing settings. If you really want a challenge, try implementing tests for other web applications using this starter project. I wish you all the best of luck in your testing and automation journey. I hope that you found this tutorial to be valuable and helpful and informative. Thank you for making it to the end. Furthermore, I'd love to hear what you thought about the tutorial and what additional tests you've written. So feel free to reach out to me on Twitter @AutomationPanda or through the contact form at automationpanda.com.